So question 2 in part A is about the classic Young's slits experiment. So first it wants the word for the process by which the waves spread out as they pass through these two narrow slits, and that word of course is diffraction, so don't get that mixed up with refraction, which is obviously something different. And then it wants an explanation for the formation of bright and dark fringes on this screen over here. So the thing with these explanation questions is that often you can really have them well rehearsed in advance, and they should then be easy marks on the paper. But the important thing is that you have to make sure you use the right words. Getting the key technical terms in there is all important. So the key things there are, first of all, that the diffracted waves, in other words these spread out waves emerging from the two slits, overlap and superposition results. Okay, because remember, when waves overlap, at any point the total displacement will be the sum of the displacements of the two individual waves. So that's the idea there. So what we're talking about here is this idea that you get these kind of waves emerging from each slit, and because you get that from both slits, you get this overlap here, and that's what's causing the interesting effects. So the first thing is that normally that would have been an important word, because you'd already had that in the first part. There wasn't a mark for that, but that's normally a key part of the explanation, and that word needs to be there, superposition. Okay, so then you have to explain what happens when superposition occurs, and remember the idea is that along different lines you'll either get constructive interference, where the waves add up to give something where the displacements are bigger than in the originals, or you get destructive interference where when you add them together they cancel out. And obviously the constructive interference is what gives you lines along which you're going to get high intensity, so that's going to give you bright fringes when it hits the screen, and along other lines you're going to get destructive interference, so that's going to give you dark fringes when you hit the screen. So what do you need to say? So you need to explain that constructive interference occurs when the superposed waves are in phase. So in phase means peak superposed on peak, trough superposed on trough. So that's a useful phrase to use, or indeed as well, you could say that this happens when the difference in path length to the screen is a whole number of wavelengths. So it would have been enough to say constructive interference happens when the superimposed waves are in phase, but you can spell that out a bit more and say, well, what has to be true for them to be in phase when at that point where they hit the screen? And the idea is that you have to have a whole number of wavelengths difference in path length so that they're arriving at completely the same point in the wave cycle. And then you really have to spell out, don't just kind of leave them to figure it out, that where you get constructive interference, that's where you get the bright fringes on the screen. So this leads to bright fringes on the screen. then you have to go on and explain explicitly where the dark fringes come from. Don't just kind of imply, well, you know, that's the other places. You have to really spell things out. So you say that destructive interference, so again that term needs to be there, occurs where the superposed waves are out of phase. And this leads to the dark fringes. You could also explain that this happens, again explain this in terms of the path length. It's a bit more difficult to express this. So this happens when the path lengths differ by an odd number of half wavelengths is probably the easiest way to put it in words. In other words, by half a wavelength, or 1.5, or 2.5, or 3.5 wavelengths, or whatever. But you can't just say by, you know, a number of half wavelengths, because 2 half wavelengths is a whole wavelength, and then you would get constructive interference. So an odd number of half wavelengths. Or you could say, you know, n plus a half wavelengths, where if n is an integer, you know, starting from 0, then you can get either half or 1.5 or whatever. That would be the sort of more concise way of putting it, but again, that's worth saying as well. The other thing that's worth mentioning is that this experiment works if the waves emerging from the 2 slits are coherent. And so it's worth just kind of including that in your discussion. So these effects depend on the 2 slits acting as coherent sources. Okay, so in part 3 it wants us to calculate the wavelength of the light given some information about distances in this setup. So the key relationship which comes from your datasheet in part 3 is that W is equal to lambda d over S. So whenever you get questions about the double slit experiment, this is the key relationship that you're going to use to calculate anything. And the important thing is that you've got to remember what these 3 numbers are. So W, remember, is the fringe width or the fringe spacing. D is the distance from the slits to the screen. And S is the separation of the slits. So you've obviously got to make sure you don't get those mixed up when you're learning how to use this. So in our case, it tells us all 3 of those things in the question, and the one we don't know is lambda. So the first job is to rearrange that equation to get lambda. So we'll just slide the S over to that side. So we get SW is equal to lambda D. And then we can slide the D down over to this side. So we get SW over D is equal to lambda. And it's really important, as in all these questions, that you do that rearrangement, write the rearranged expression down, and only then do you put numbers into it. If you go straight in with the numbers, then if you get it wrong, you're going to struggle to get marks for working. So write down the rearranged relationship. So S is the separation of the slits, and it tells us in the question that that was 0.56 millimeters. So we've got that S is that number of millimeters, but as in all these questions, the important thing is turning that into the SI unit, which is meters. So that's 0.56 times 10 to the minus 3 meters. So that's 0.56 times 10 to the minus 3. Now W is the fringe spacing. So if we think about what that means, remember, so if this is the sort of intensity of the light as you go across the screen, what you see is sort of something like this. Okay, so that would be the maximum of a bright fringe, and then a dark fringe, and then a bright fringe, and then a dark fringe. And W is simply the distance between one maximum and the next. Or if you prefer, one minimum and the next, it doesn't matter which, because it's the same in this setup. So that's what W is, but what it's told you in this case is the value for 4 fringe spacings. So in other words, it would be the distance not just across there, but it would be from there to that's 1, 2, 3, 4. Okay, so it's 4 spacings. And so obviously in order to get W, we have to divide by 4. So W is going to be 3.6 millimeters. It says it's 4 spacings, so it's 3.6 divided by 4, which is 0.9 millimeters. Okay, so we can put that into there, and again the important thing is that's got to go into meters. So 0.9 times 10 to the minus 3 meters goes onto there. And then D is the distance from the screen, from the slits to the screen, which it tells us is 0.80 meters, so that one can go straight in because it's already in the right units. So those are the numbers we get, and if you plug those in, you get 6.3 times 10 to the minus 7. And that's the wavelength in meters. And so that's your answer. Part B is asking us what difference it would make if, instead of doing this with red light, which is what was happening in the original experiment, we had white light. And white obviously contains not just a single wavelength but a whole range of wavelengths, from sort of red at one end to violet at the other, so it's a whole mixture of different wavelengths. So this is all about the path length difference thing. So the first thing to realise is that the central bright fringe is the one that's in line with the sort of midpoint between the slits there. And the point is that the path length there from this slit and from that slit is the same. Right, so that central bright fringe, the path length is equal, so it differs by 0 wavelengths, and that will be true whatever the wavelength is. Okay, so that will be, the path length is the same for both, so it's 0 times the wavelength of red light and it's 0 times the wavelength of blue light. So all of the wavelengths, you will get no path length difference and therefore constructive interference at that point. So the central fringe at that point will be white, because all of the colours, okay, all wavelengths give constructive interference. Because there's no path difference for that one. Now if we go out to the side and say, right, what about the next fringe out? Well, the next fringe out will occur where there is a difference of one whole wavelength between the path length from one and the path length for the next. So in other words, if it was, say, over here somewhere, these would now be the two path lengths, and obviously this one is longer than that one, but if the difference is one wavelength, then they're still going to arrive in phase at this point, so you're still going to get constructive interference. So this is the n equals 1 fringe, and the path length difference is one wavelength. But what if we have a different coloured light this time? So if that's our violet light, the path length difference between here and here is 1 times, 350 nanometers, or whatever the wavelength of our violet light would be. But suppose we have red light, where we have a much longer wavelength. What does that mean? Well, what it means is that to get we need to have a bigger difference between the path length of this one and this one to correspond to the bigger wavelength, and that's going to mean basically that fringe gets to go further out. So you would get this kind of thing. Okay, where in order to get a bigger path length difference between this one and this one, the fringe ends up being further away from the central one. Okay, so what happens then for all of these fringes other than the middle one is that, so all other fringes appear as a continuous spectrum of colours, because each different wavelength will have a slightly different point where the path length difference is a whole number of wavelengths. So all the other fringes appear as a continuous spectrum of colours, and red will be furthest from the centre, or from the central fringe, and violet at the other end of the spectrum will be closest. Okay, so those are the key things that you have to get then. First of all, that the central fringe is going to be white. You didn't have to explain why in this question, but you may have to, so make sure that you can explain that that's because there's no path difference. But for all of the other fringes, in order to get a path length difference, which is a whole number of wavelengths, you'll get slightly different positions on the screen where that condition is realised. And in particular, the shorter the wavelength, the closer that will be into the centre. So each of these fringes, instead of appearing white, the colours will be spread out a little bit, and so you get a continuous spectrum appearing for each fringe. The other way you can think about that, rather than sort of thinking about the sort of construction like that, is just to think about this equation, because that leads you to the same conclusion, that the width W, which is the spacing between adjacent bright fringes, is proportional to lambda. So in other words, the longer the wavelength, the more widely the fringes will be separated, and that gives you the same result, that because red has a longer wavelength than blue, the red one, the bright peak will be further from the central fringe than it will be for violet at the other end of the spectrum. So you can get the same result from there, that the red is shifted further away in that first fringe, and indeed in all of the fringes, than the violet would be, just by looking at that equation.